All right. So we're going to begin electrostatics by talking about the most familiar quantity, and that is force. So we can define the electric force between two particles using Coulomb's law, which states that the electric force is proportional to the product of the two charges and inversely proportional to the square of their center-to-center separation. And we give ourselves an r hat vector showing the force is going to be radial. So positive and positive are going to directly repel, so that would be the positive r hat direction, and positive and negative attract. So that would be the negative r hat. So because force is a vector, we're not actually going to include signs anywhere. Instead, we'll just attach an appropriate vector. So we'll write ourselves a note here that we put no signs into Coulomb's law because it is a vector. And vectors aren't positive or negative, vectors just have direction. So sometimes we won't even state this absolute value, and it's just implied that we just take the magnitude of everything and just attach on a unit vector. The constant k is called the Coulomb constant. It's approximately 9 times 10 to the ninth in SI units, although we might write it differently in terms of a more fundamental constant, the permittivity of free space epsilon naught. So you might see it used interchangeably with this 1 over 4 pi epsilon naught out in front. That is the same as the Coulomb constant k. So let's just begin with a little ranking task. So we have a bunch of different charges with their separations. So we have two q's separated by d. We have a q and a q over 2 separated by d. We have two sets of 2q separated by 2d. And we have an 8q and a q over 2 separated by 2d. So our first question just wants us to rank the magnitude of the force experienced by the left charge in each set. All right, there's a variety of ways to do this. I'm just going to do it fully symbolic in each of these cases. So we do know that our expression for electric force says the magnitude of the electric force is equal to a constant k times the product of the two charges and divided by the square of their distance. So in case A, we of course have our Coulomb k. Both charges are q, and the distance is d. So I get sort of the base case of Coulomb's law, kq squared over d squared. Then for case B, we have our k, we have a 2q, we have a q over 2, and we still have a d. So the 2q and the q over 2, well, that makes 1. So this is also kq squared over d squared. Then case C, we have a k, a 2q, a 2q, and a 2d. So here's where we have to be careful, and we have to do the inverse square law. Because in this case, yes, I get 2 times 2 equals 4 on top, but also I have to square the 2 that's attached to this d. So that makes a 4d squared on bottom, so I get a 4 on top, 4 on bottom, so this also makes kq squared over d squared. So we can definitely guess what this last one is going to be, although it would be kind of mean for me to make 3 of them tie, and the fourth one not. So we get a k, an 8q, a q over 2, and a 2d all squared. So we can see the 8 and the 1/2 make a 4 on top again, and squaring the 2d quantity gives me a 4 on the bottom. So this, of course, will make kq squared over d squared again. So notice that in all 4 cases, the changes to the charges and distance exactly balanced out. So in all 4 cases, the force will be equal. And justify our ranking, well, we just proved it. In each case, we're just saying that the force was equal to kq squared over d squared. And maybe I should say the magnitude. What if instead we wanted to rank the magnitude of the electric force experienced by the right charge? So I kind of glossed over this fact that we're looking at the left charge, but really it doesn't matter. And we can reason this 2 different ways. So first way, we can reason through why there will be no change to this ranking is just through Newton's third law. Because if I have 2 charges that are interacting, doesn't matter what is the same or different about them, this is going to be repulsive. So it doesn't matter what's the same about them, doesn't matter what their mass is, doesn't matter what their charge is. Newton's third law guarantees that these charges will always experience equal forces oriented in opposite directions due to the other. And we can also prove this using Coulomb's law, because the equation for Coulomb's law says that force is proportional to Q1 times Q2, which means it doesn't depend on just Q1 or just Q2. It depends on their multiplication. And we know that multiplication, the order doesn't matter. So since the force depends on the product of each charge, and order doesn't matter, well, the force must be the same, regardless of which one we pick to be Q1 and which one we pick to be Q2. Now, here's a typical Coulomb's law vector addition problem. We have 3-point charges of mass m equally spaced along the axis, and we're interested in indicating the direction of the net force on the particle with charge q, so that leftward charge here. Justify our answer without manipulating equations. So, first of all, I know that the net result is going to be the vector sum of the forces from each charge. So I do know that due to the rules of attraction, the negative charge is going to attract the positive because opposites attract here. So this is the force from the minus 2q. And then we also have the force from the plus 4q that's repulsive. So first, notice that the 4q is twice as charged. So its numerator will get larger. But also the distance is doubled as well. And those effects don't cancel because force is proportional to 1 over r squared. So doubling the distance actually does more to decrease the force than doubling the charge does to increase it, because charge is linear on top, but distance is quadratic. So actually we know for sure that this repulsive force from the 4q is actually going to be less. So we can see the blue arrow is longer, so we're going to get a rightward net force. And there's my explanation. So the 2q charge pulls right, the 4q pushes left. The 4q charge is twice as charged, but it's twice as far. And due to the fact that the distance is squared, that farther away part causes a larger effect. So now we want to derive an expression for the initial acceleration of the particle we just looked at. So if we want acceleration, we know it's a force situation with Newton's laws. So let's just start with that. So let's start by finding the net force on the particle. So first, I do know that my net force is going to be the vector sum of the force from the 2q added with the force from the 4q. And here's where we will do stuff with some signs. So I'm going to attach some unit vectors to each of these now. So for my 2q charge, my force magnitude will be a k times the q times the 2q, and it's just separated by a distance d. And then for my direction, since I drew it correctly on the picture, I know I'm just going to put a right unit vector or an I hat to indicate that. And then similarly for my 4q charge, this one actually is directed to the left, so I would attach on a minus I hat into that one. And the distance here would be 2d because it's 2 charges away. So now we can go ahead and just do some simplifying here. So my net force would be 2kq squared over d squared right plus, well, the 4 on the top is going to get balanced out by the 2 squared on the bottom. So this is actually just 1 kq squared over d squared left. So that actually just places my net force as just kq squared over d squared to the right. And now it wants the initial acceleration, so we can just use Newton's second law that says acceleration is F net divided by M. So I just divide an M into my expression. So this is just KQ squared over MD squared, and it is directed to the right. All right, is this consistent with our selection in part A? Well, we just said this particle is going to accelerate to the right. And in part A, we said that the net force is to the right. So that makes sense because Newton's second law says acceleration and net force are proportional. So it's consistent because acceleration is to the right. And by Newton's second law, we know that acceleration and net force are proportional. So we get a rightward net force as expected. So one thing we looked at with the definition of Coulomb's law is that this R in Coulomb's law is actually the center to center distance. So we're going to use two variations of this idea called the shell theorem. First idea of the shell theorem is that charges will only feel forces from charged objects that are sort of within them. So, for example, this charge will not feel a force at all from the shell because it is inside. So this is just like the fact that there's no gravity inside the planet. The only thing that could affect this is if there was charge sort of under it. And the second shell theorem says that if you do have a spherical object, you can just shrink it down and put all of its charge at the center. So all spheres can get shrunk to points. Again, this is also something we do with planets. Makes sense because the inverse square law still holds. If a point charge is placed a distance 0.3 meters from the outside edge of a conducting sphere of radius 0.1 meters, and we're given the charge on each object, calculate the force. So let's fill in some dimensions here. So we're given that a point charge is placed 0.3 meters from the edge of a conducting sphere of radius 0.1 meters. So this was our situation that we're given, and we also know the value of Q. So Q was given to be 8 microcoulombs. And again, the prefix micro means 10 to the minus 6th. So now we can use shell theorem to get the answer to this, to find the force. Because shell theorem says if you have any spheres, you can just shrink them to a point. So if I do that here, I might show that this was originally a sphere that got shrunk down here. Well, I just have a new distance now. It's just the center to center distance, which is 0.3 plus 0.1, which makes 0.4 meters. And the charge can all be concentrated at the center. So this is 8 microcoulombs, and this is also 8 microcoulombs. So now we can just do Coulomb's law, just being careful with that center to center distance. So the force is just going to be kq squared over r squared, because both charges were the same. The Coulomb constant k is 9 times 10 to the 9th. 8 microcoulombs is 8 times 10 to the minus 6th coulombs. And r is 0.4 meters. So we square that. So after doing all this and plugging in, we end up getting a nice answer of 3.6 newtons. So again, we can just shrink it down and make it center to center. Instead of defining charge, we might also define something known as charge density. And there's 3 types of density we could encounter. We have linear charge density lambda, which is charge on a one-dimensional object or a length. So this is almost always a rod or some sort of an arc, which is just a bent rod. Then we have surface charge density sigma. That's our charge per area. So that's usually our charge plates are on the surface of something. And then our volume charge density rho. That's just if you have charge all throughout an object. This is very similar to the mass density from chemistry class. So if we want to convert from density to charge, you just multiply by its namesake size. Because you can always write that sort of the amount of something is equal to some sort of a density times some sort of a size. Because that's what density is. It's the amount of stuff per some sort of measurement. So you can always get the charge by multiplying the relevant density by the size. So here's some practice with density functions. So an insulating sphere and a conducting sphere both have radius r. The insulating sphere has volume charge density, rho, and the conducting sphere has a surface charge density, sigma. And they're both radius r. So we'll definitely need this later, but if they both have radius r, that means that the distance between the centers of the spheres is going to be 2r, because it takes one radius to get to the meeting point and then another to get to the other center. And now we can do some expressions here. So first, charge in the insulating sphere. So the insulating sphere had density rho. So charge, if it's a volume density, is the volume density times the volume. And volume of a sphere is 4/3 pi r cubed. So our charge on the insulating sphere is 4/3 rho pi big R cubed. All right. Charge on the conducting sphere. So this was an area density on a surface area. So it's sigma times the surface area of the sphere, 4 pi r squared. So we just get 4 pi sigma r squared. Now we can find actually the force between the spheres because we know each of their charges. So F is equal to K Q1, Q2 over the distance between them squared. So Coulomb K is just K. The charge on the sphere that was insulating is 4/3 pi rho r cubed. And the charge on the conducting sphere with surface charge density was 4 pi sigma r squared. And the distance between the two was 2r. So I have to square that entire thing. Because again, we use shell theorem here, center to center distance. Now we can break this down. We can do some simplifying here. So on top, I would get 16/3, and then I'd get a pi squared, I'd get a k, I'd get a rho, I'd get a sigma, and I would get 5 copies of the radius. And then on the bottom, I would have to remember to square the 2. And I would get 4r quantity squared on the bottom. So now we can simplify this, and we will get, well, the 4's cancel and 2 of the r's cancel. So I get 4/3 pi squared k rho sigma r cubed. That is a lot of letters. So now we're just going to look at how does this actually depend on the radius of the sphere? Well, we see that in this case, the force actually increases with radius of the sphere cubed. And how could we figure this out without deriving anything? Well, if we look at this without deriving anything, we see that the force is proportional to both charges divided by the distance between them squared. So Q1 is a volume charge density, so this is proportional to the volume. Q2 is an area charge density, so that's proportional to area. And the distance between them squared, of course, that was just proportional to their radius. So volume is proportional to big R cubed. Area is proportional to big R squared. Distance, of course, that's going to be proportional to the radius, so squaring that gets us a square. So we do actually see that we get this as proportional to the radius cubed, as expected. All right, now for some force balancing. So we have two spheres, their center to center distance is d, and we're going to be interested in drawing some free body diagrams here. So one of them's hanging, one of them's on the ground. So first of all, for our hanging sphere, both of these spheres do have mass, so it is going to experience a gravitational force, mg, downwards, and it's also going to experience an attractive electric force downwards. And then since the sphere is balanced, that must mean that there is a tension force up that is balancing the two of these. So tension will balance the combination of the weight and electric force. Whereas for the bottom sphere, we see that there is a weight force down. There's an electric force up. Again, those equal and opposite pairs. And then it will experience a normal force from the ground that sort of makes up the difference. So now we can put this on a grid. So again, since we're given a grid, it means we need to be able to show some things. So I might give my weight 2 ticks. And these spheres are identical, so I'm going to do both at the same time for that. This one only has 1 force, so I don't need to save that much space here. Then I might make my electric force between the spheres just 1 tick. And these do have to be the same. You have to show that Newton's third law pair here, equal and opposite. I totally just picked an arbitrary number with 2 and 1 here. And now I can make up the differences to make my forces balance. So in my top sphere, my tension must balance both of the downward forces, so I will make this the sum of the other two. And then my normal force needs to balance the difference between the weight and what help it got from the electric force. So we could just stop here and write some Newton's first law equations for each sphere. So both of these are balanced. So we can just set some force balancing equations up. So for the top sphere, we know tension is the combined value of the weight and the electric force. And then for the bottom sphere, we know that normal and electric force combine to balance the weight. So now we can derive some expressions. So we just said in the previous part that the tension force balances both the gravitational and electric forces. And our expression for the gravitational force is mg, and we can use Coulomb's law, kqqq over r squared, or d in this case, to get an expression for that force. Now for the normal force, we use our other equation that says normal force and the electric force combine to balance the weight. So the normal force is just going to be equal to the weight minus the electric force, so mg minus kq squared over d squared. And actually notice that there exists a point where you could bring these charges so close together that this kq squared over d squared electric force actually balances mg, and you could levitate the sphere and get it to escape the ground. All right, suppose instead we replace the bottom sphere with a negatively charged one instead of a positive. So originally they're opposite. Now let's look at what they do if they're the same sign. So in this case, we're looking at what would happen if both of the spheres were negatively charged. So of course, both of the spheres would still have weight. But this time there's going to be an upwards electric force on the top sphere because it's repulsive instead of attractive. So now notice that tension force doesn't need to be nearly as long as it was before, which is what this question is actually going to ask. What happens to tension in the string if we do this with with charges of the same sign instead of opposite signs? And then if we just for fun did a force diagram for the bottom one, it still has weight, but it's actually getting pushed harder into the ground than before due to that repulsive force. So its normal force actually needs to get greater than before. So we see that the tension force actually gets shorter than what it had to be before, and the normal force on the other sphere actually increases. So if the bottom charge is reversed, the electric force becomes repulsive. So the electric force acts upwards on the top sphere. So tension is going to decrease because the electric force is sort of helping out the rope a bit. So the rope doesn't need to pull upwards as hard because there's another force helping. Now we'll bump it up to 2 dimensions. 3-point charges are placed at the vertices of a square of side length s. And we're first interested in the direction of the force at the charge placed at the bottom left corner. So as with anything, as with the first force problem we did with multiple charges, we will do vector addition. So notice that I have two charges, and they are the same distance away. So I don't have to deal with distance at all as a factor in my comparison. But one of these charges is bigger than the other. So I know that my green charge plus Q is going to exert a force downwards. But my 3Q charge is going to exert a force leftwards, but it's actually going to be 3 times as long. So in our part A, we're actually going to draw this direction of the net force of a charge placed at the bottom left corner of the square. And it's not just down and to the left. We have to be more precise. We have to narrow it down to sort of what component is longer. Is it more left or more down? And we can totally do that. Because really what we've just figured out is that our net force is going to be sort of 3 ticks left, but only 1 tick down. So we can see that we're definitely well above that 45-degree line in quadrant 3. So that is going to place us anywhere in sort of this region. And we can reason through it just like we did here. 3Q charge pushes left, plus Q charge pushes down. 3Q is bigger, so the leftward component is bigger. So therefore, it's a down and left force, but the left component is bigger. Now let's find its magnitude. Well, we can sort of work this out just like we did before, where we're going to look at each force separately. So we know that our force from just the Q, well, that's just going to be KQ squared over S squared. And this was directed down. And then our force from the 3Q is going to be, well, K times Q times 3Q, so that's a 3 KQ squared over S squared, and that's directed left. So our net force would be 3 KQ squared over S squared left plus KQ squared over S squared down, but we actually want the magnitude. So anytime we want the magnitude, it's probably a Pythagorean theorem situation, and it definitely is in this case. So I'm going to draw myself a nice long force here. So this is 3 KQ squared over S squared. And then my downward force is only 1 KQ squared over S squared. And I'm interested in calculating this slant length right here. And this is a right triangle, regardless of how I drew it. So we can just find its magnitude using the Pythagorean theorem. So don't actually plug the whole symbol stuff into the Pythagorean theorem, because you know the units are going to work out, because both of these have units of KQ squared over S squared. So we can just do the Pythagorean theorem with the coefficients. So I know that my magnitude of the net force is going to be, well, we know the units are KQ squared over S squared, and then for the coefficient in front, we just do the Pythagorean theorem. 3 squared plus 1 squared. So this makes 3 squared is 9, so 9 plus 1 is 10, so I get square root of 10 KQ squared over S squared as my force. Now let's calculate the angle that the force vector makes with the positive x-axis. So once again, we're going to use this fact that we don't need to really put the units because they're going to match. So we said that this is where our force lives, right here. So maybe I'll define this angle inside this triangle right here to be phi. So we can see that the tangent of phi is going to be equal to 1/3. So this angle phi inside the triangle is just going to be arctan or inverse tangent of 1/3. And that's going to be roughly like 18 degrees. Let's get it to 1 decimal point. 18.4 degrees. And if we want the angle theta that this makes with the x-axis, which is going to be this angle, well, that means that my angle theta is just going to be 180 degrees plus this extra triangle angle here, and that makes 198.4 degrees. And why we ask to actually calculate this is the consistency question. Is this consistent with what we did in part A? Well, our answer is 198.4 degrees. And 198 is definitely between 180 and 225. So we get our angle inside the range that we expect. Now, this is a classic you gotta know it type problem. We got some charges arranged in a triangle. So first, we're going to draw ourselves some force vectors showing the net force on each charge. So we can do that over here. We'll show the net force. We'll show all the individual forces on this sort of original triangle here. So let's name my charges here. So for my blue charge is going to push directly away on both the others. My green charge is going to push directly away on the others. I'm trying my best to make the magnitudes about the same. And then my purple charge is also going to push directly away on the others. All right. So now we can try to estimate the net force direction on each of these. So the only one that we can definitively say is this top charge is definitely getting pushed straight up. Because by symmetry, notice that there's equal pushes to the left and right. And if there's equal pushes to the left and right, that just leaves the two vertical pushes that are going to add. Then for my left vertex, it gets pushed left and down left. So it's going to go down into the left, but actually more left. And then same thing with the right. It's going to go right and down right. So it's going to be just down into the right, but mostly right. So it's supposed to mirror the left charge. So I might actually make that look a bit better here. Close enough. So let's actually solve for the net force magnitude on the one that's easy to do, the top charge. So with situations like this, you have to do a bit of work yourself to figure out sort of what's actually contributing. And in this case, it is not the whole force we want. We want just the vertical push, and we want to double the vertical push from one of the charges. Because we see what's actually adding to the force is we have this push and this push are adding. Because the horizontal pieces, well, these are doing nothing, because these are just canceling. So I can actually begin my derivation just by writing out that the net electric force is just going to be 2 times the y component of the force from one charge. So, and if you're extracting a component, we know the trick is always to multiply by the full force and then multiply by a relevant angle. So this is actually an equilateral triangle, which is a key to the problem, because if this is an equilateral triangle, then this is 60 degrees. All of these angles are 60 degrees, but we're going to look at this one. So if I want the vertical piece of something with this 60-degree angle, well, of course, that's going to be the opposite leg. So I'm going to tack on a sine of 60 degrees to this expression. So our force is just kqq over s squared, so kq squared over s squared. And then what is sine of 60? Is it 1/2 or root 3 over 2? Well, it's root 3 over 2. That's actually in the table of information. You could have looked that up. So we get the 2 and the 2 cancel, so we get root 3. kq squared over s squared is our magnitude. And for the direction, it's just directly up. Now let's actually model the motion of this. So at t equals 0, the top charge is released from rest. So we launch this charge away, and we let the others stay there, and we're interested in graphing the acceleration as a function of time and the velocity. So first, we know that the force, the electric force, is proportional to distance squared, 1 over distance squared. So since the force is decreasing as the charge gets farther and farther away, this means that A is going to decrease with time. And for the extreme case, you know that we're going to get 0 acceleration if we're very, very far away. And then we also know that at time equals 0, we're going to accelerate. So this is just any sort of decaying exponential. And maybe I can make that a bit better. Maybe I'll decay it a bit faster here. Good enough. Then for velocity, we can think about it using a calculus approach, or I'll just do a conceptual approach. So we do know that I'm going to start at the origin because I'm not moving. And at the end, I'm not going to be pushed anymore, so I'm not changing my speed. So what we actually get is, since we know the pushing or the force is going to decrease over time, I'd start with a steep slope, then I'd get a shallower slope, then I get a shallower slope, then I get a shallower slope, and so on. So my velocity is actually going to cap out. So this is going to make some sort of curve with a horizontal asymptote. So something like this. And maybe I should be a bit more clear and indicate that there will actually be a horizontal asymptote on this curve. No, I don't want that. I want just a, yeah, that's what I want. So maybe something like that, just to show that there's going to be this horizontal asymptote that I can't cross. All right, and lastly, we'll do a 2D example with some trigonometry. This is also a classic. So we have two balloons from a Van der Graaf generator. That's a typo. And they're just balanced at rest in this situation. So what's going to happen here is we know that there's going to be a tension force pulling this balloon up. There's a gravitational force pulling this balloon down, and there's an electric force repelling this balloon. And by symmetry, it's just reflected on the other side. So if we're drawing a free body diagram for the leftmost hanging balloon, since the tension is influenced by the other two forces, I might give myself 3 ticks down for the gravitational force, 2 ticks to the left for the electric force, and then tension, well, the x component of tension has to balance the electric force. So we know we're getting 2 units left, or sorry, 2 units right. And then the gravitational force gets balanced by the vertical component, so that's going to be 1, 2, 3 units up. So my tension is going to be, I actually need to find the point here, like that. Because you can check that it balances both the electric and gravitational forces. So now let's try to actually solve for some things here. So first, let's find the magnitude of the tension force. And what'll help here is to use vector addition, because we know that these vectors have to add to 0. So my tension force, which was up and at an angle, my gravitational force, which was straight down, and my electric force, which was to the left, need to add together to make no net force. So, since this is a nice right triangle, if we just want the tension in the string, we just hit it with a little Pythagorean theorem. So this is the square root of fg squared plus fe squared. But those aren't allowed. We want to do this in terms of the m's and q's. So, of course, fg is mg, and fe is kq squared over d squared. So that's actually going to be our tension, is just the sort of Pythagorean sum of the vertical and horizontal forces. Then let's derive an expression for tan theta in terms of the given quantities. And we're going to copy this triangle down here because we'll see this is actually very helpful for us. So I drew this triangle because we define the angle theta as the angle between tension and the vertical. So that's why I drew my triangle like this, because I can actually put my theta right back in here, because it's between tension and the vertical. So tan theta is just going to be opposite, Fe, divided by adjacent, Fg, which is going to be kq squared over d squared, divided by mg. So this tells me that tan theta is equal to kq squared over mgd squared. And now we can solve for the charge on one of the balloons in terms of theta. So that's kind of why we did this tan theta trick, because tan is the trig function that doesn't involve the hypotenuse, which we didn't know. So we're given from this previous derivation that tan theta is just kq squared over mgd squared. And if we're solving for the charge q, I can multiply everybody on the denominator over. So then by dividing by k and then taking the square root, I'd get my charge q is just the square root of mg d squared tan theta, all divided by the Coulomb constant k. And I ask this question because it's a lab we can actually do in class to varying degrees of success with these balloons. Because we can get that expression for tan theta just by using rulers. All right, last little aspect here. Suppose the mass of the balloons are increased and I change the string length so the d stays the same. What will happen to my angle? So it is important to note theta is the angle from the vertical. So let's just show maybe my original case here. Definitely exaggerating it a bit, but this was my first case where this was theta. So we're interested in asking what happens if I actually do a much, much heavier balloon at the same distance. So first of all, we know that the electric force is going to stay the same. So it's going to get pushed the same amount horizontally. But if I have a heavier balloon, that's going to add to the vertical force. So it's actually going to drag the string to make it more vertical. So if I have a heavier balloon with more mass, that's going to drag this theta value down. And you can think about the extreme case. Or if I have a really, really heavy balloon, most of your tension is going to be distributed to making that balloon actually hang vertically to balance the weight. So what we'll actually get in this case is that theta is going to decrease because your string is going to go towards the vertical. So increasing the mass of the balloon increases weight, but not the electric force. So you're just going to have to increase your vertical component of tension, which means your string needs to be angled more vertically than before. So the angle from the vertical will therefore decrease. And this is much easier to justify quantitatively, because we said earlier that tan theta, the tangent of this angle from the vertical, was equal to kq squared divided by mgd squared. So we can see here that tan theta is proportional to 1 over m. And we did say that d stayed the same. So this means that as m increases, tan theta is going to decrease. And if we look at the graph of tan theta increases when theta increases. So this means that theta also decreases, which is what we expect. So that's it. There's some Coulomb's law for us.